Hello, welcome back. So now in this part, we will solve the problem related to the helically reinforced column. So this is our problem which we have to design. So in this, we have to design a circular RCC column to support an axial load of 1100 kilonewton. And we have to provide helical reinforcement in the form of helix in this column. And the material here is concrete and steel, and the grade of concrete is M20 and steel is HYSD steel bar. So until and unless mentioned, we will consider this as FE415. And unsupported length of column is given here, which is 4 meter. And also the end conditions is given, which is column is fixed at both ends. So this condition is given to calculate the effective length of column. So here all the data is given. So we will write first the data given here, and then we will follow the same process that we have followed in the previous example. So now our first step is to determine the permissible stresses. So here we will determine sigma C and sigma SC. So we can find that in by referring table 21 and 22. So I have explained this. How do we find out that in the previous example? So here I will put the values directly here. So for M20 grade of concrete, sigma CC is 5 Newton per mm square, and for Fe415 steel, sigma SC value is 190 Newton per mm square. Then the next step is total axial load on the column. So it is also given in the example. So the total load is 1100 kilonewton. And because we don't have the sufficient data to find out the self weight of column, so we will assume here that this load is inclusive of its self weight. So that is the step 2. Now in the step 3, we will try to find out what should be the cross-sectional area of column to carry this load. So as per equation 2, so the equation that I have shown you in the previous part, so the equation will be multiplied with the factor 1.05. So this time we will use this equation, and in this equation sigma cc is already given, AC is the area of concrete here, and ASC is the area of steel. So as I have explained earlier also, that we know that AG is the summation of ASC plus AC. ASC is the area of steel in compression and AC is the area of concrete. So here first we will assume the percentage of ASC, say 1%. So it means 99% of AG will be AC and 1% of AG will be ASC. So here we will write the value in terms of AG, because here we want to find out the AG value. So we will write AC in terms of AG as 0.99 AG and ASC as 0.01 AG, because we will assume that ASC, area of steel, here is 1%. So at 1% of steel, what should be the area of cross section of the column? So that we will try to find out. So here, this is what I have explained you. We will assume that ASC is 1% of AG, and we can write this in this form also. And similarly, for concrete, it will be 0.99 AC. So we will put here in the equation. So by putting the equation, the only variable, though the only unknown is AG. So now solving this equation, we get the AG as this area. So now this is the gross cross-sectional area this is the gross cross-sectional area of the column. Now we have to find out the dimension of the column cross-sectional dimension of the column. And because our column is circular, so here we need to find out the diameter of the column. So diameter of the column can be found by this relation. So we know that AG will be pi d square by 4, because it is a circular column. So here we can find out d by rearranging this term to this one. So putting the value AG as this value, so we get the dia of column as 441.38. So now we will round off this value to the lower side, and I have explained earlier why do we round off the dimension of the column to the lower side, because if we round off to the higher side, then percentage of steel may decrease and it may be less than 0.8%. So therefore, we generally adopt the dimension to the lower side. So here we will adopt our diameter of column as 400 mm. So that is step 4. Now we will move to the next step, which is step 5. So here we will find out the effective length of column, and basically to check whether our column is long column or short column. So that we can check by calculating the slenderness ratio. So here effective length depends on the end conditions, and in our question it is already mentioned that column is fixed, and for fixed condition the effective length is 0.65 times of L, and L is the unsupported length which is already given in the problem, which is 4 meter. So by putting the value L as 4 meter, we get effective length as 2.6 meter. And now we will find out the slenderness ratio, which is the effective length by least lateral dimension. So here the lateral dimension is the dia of column, which is 400. So the lambda is 6.5 and it is less than 12. So therefore the column is short column. So now we can say our column is the short column. So now we will move to the next step, which is about the calculation of longitudinal reinforcement. So here in this case, again we will use the equation 2, and this time in this we have to rearrange our equation such that the unknown will be ASC. So here what we can do is, we know that AG is the sum of area of steel in compression plus AC. So this time we can replace AC with AG minus ASC. So here ASC is the unknown value and AG is the gross cross-sectional area. So therefore we will use that in the equation again. So this is our equation. So here we will replace AC by this AG minus ASC. So the equation will be this. So P is already given, and here we have written AC in terms of AG and ASC. Now AG is the new cross-sectional area of the column. So now we have adopted our diameter of column as 400 mm. So the AG will be pi by 4 into the adopted dia, pi d square by 4. So here the d will be 400 mm square, and ASC will be the unknown value here. So by putting this value, we can calculate ASC as 226.49 mm square. So this is our area of steel in compression required in the column. So we have to distribute this area into the number of bars, and we know that minimum number of bars in the circular column will be 6. So we have to select our dia such that at least 6 bar should be there. So now assuming the dia of bar as 20 mm dia, 22 mm dia bar, and the number of bars can be calculated as total area of steel in compression divided by area of cross section of 1 bar. So that is what I have written here, and the number of bars comes out in this case is 5.96. So it is roughly 6 bars. So yes, minimum number of bars in the circular column is 6 bars. So it means the dia adopted is same. In case if the number of bars is coming low or higher, so accordingly we can change the dia of bar so that we can have optimal number of bars in our column. So now as you can see, we have approximated this value to 6. So therefore ASC provided will be slightly higher than the required. So we can find out that, so the ASC required, ASC provided here is 2280. So now we will find out what is the percentage of this area in our cross section in our column. So the percentage is 1.82. So now you can see this percentage is greater than 0.8% and less than 6%. So therefore the percentage provided in the percentage of steel provided in the column is okay. So now moving to the next step. Yes, number of bars is not less than 6, so therefore it is also okay. So now move to the next step. So here this is the step where we will be changing, where we will be having different calculation, because this is our circular column with helical reinforcement. So here we will apply the helical reinforcement rules that I have explained in the previous part. So first of all, we have to assume the diameter of the spiral bar. So the same condition we can apply here like we have used in the previous case in case of lateral ties. So minimum dia of bar, as per condition, it will be 8 mm. And then the main thing that we have to find out is the pitch of the spiral or pitch of the helix. So I have explained the equation. So we will be using the same equation to find out this pitch. So first we have to find out what is the value of DC and phi SP. We have just assumed as 8 mm dia because the minimum dia of bar in HYSD bar is 8 mm. So we are taking that value. And ASP is the area of cross section of this spiral bar, and FY is 415. D is the dia of column, which is 400. So here we need to find out first what will be the value of DC. So we know that DC is measured from the edge of this spiral to the edge of this spiral. So the clear cover we will assume here as 40 mm. So therefore the DC will be D minus 2 times of 40, 2 times of clear cover. So the DC value becomes, sorry, it will be 320. It will be 320 mm. And phi SP, as I said, we have phi SP, which is the dia of spiral as 8 mm. Now we will find out the ASP also. ASP is the area of cross section of spiral bar, which is pi d square by 4. So it will be pi d square by 4, and the area of cross section of spiral bar will be 50.24 mm square. So now we will put all these value in this equation, and here FCK value will be 20, FY value will be 415. So all the values now known. So we will now put all the values in the equation and calculate the pitch. So pitch calculated is 62.67 mm. Now we have to check this pitch with the IS code limits. So what is the limits? So we will see what is the maximum pitch limit and what is the minimum pitch limit. So first we will see what is the maximum spacing or maximum pitch limit. So criteria 1. So it says pitch should not be greater than 75 mm. Also, second criteria is core diameter divided by 6. So 1/6 of the core dia, which is 320 by 6. And as per this condition, the pitch comes out is 53.33. Similarly, we have the minimum spacing or minimum pitch limit also. So as per minimum pitch, the first criteria is it should not be less than 25 mm, and the second criteria is 3 times of the dia of the spiral or helix. So it is 3 times of 8, which is 24 mm. So here ultimately we fall into this limit, which means our pitch should not be greater than 53.33 mm and it should not be less than 24 mm. So ultimately our pitch should be in between this value as per IS code recommendation. But as per calculation, our pitch is 62.67 mm. So therefore, what we have to do is we have to select our pitch in between these two values because our calculated pitch is higher than this value. So therefore, it is not satisfying the IS code recommendation. So therefore, we have to select our pitch in between 53 and 24. So let's say we adopt the pitch as 50 mm. So the round figure for the pitch as 50 mm. If we select lower value of the pitch, so in the case we have to provide higher length of the spiral and also there may be some congestion. So therefore to avoid that, I have adopted this 50 center to center as the helix. So this is how we calculate the transverse reinforcement in case of this type of column. So this is the final reinforcement sketch that we have to make. So here, these are the 6 bars that we have designed as longitudinal reinforcement. And this is the this is the spiral. And in the elevation also, you can see how it is varying. So that is the reinforcement sketch. So it concludes our numerical. So thank you. Thank you.